Alright guys, so what we're starting today is the last chapter that we're going to be covering in Trig. This chapter will take up the last 3 weeks, and this will be it. Now, most of this chapter, a good part of this chapter, isn't going to be anything new, because we've covered complex numbers before. You've covered them in Algebra 2. So a lot of the stuff that we covered in Algebra 2 will show up again, but there's going to be other parts that we can use Trig to solve with complex numbers that you haven't done before. So there'll be a little bit of stuff new and a little bit of stuff that's not so new. And today, everything we're going to cover is not going to be anything new. It's not going to be anything you haven't learned before. So hopefully today's not going to be too bad. Now, the first part, when we define a complex number in standard form, we have A, which is the real part, and B is the imaginary part. And it comes in the standard form of A plus BI. So any complex number can be written in the form of A plus BI, where A is the real part and B is the imaginary part. When B is not equal to 0, this is the imaginary number. The number BI, where B is different from 0, is called the pure imaginary part. So we have the real and imaginary parts of a complex number. Because when we combine them together, we do get a complex number. This is true because every real number can be written as a complex number. So we have this as part of the fundamental theorem of algebra, that every solution has a complex solution. It's just that the complex solution is 0i. So we can make any number a complex number. It's just the complex or the imaginary part is 0. So the first thing we're looking at, I think that there's probably an extra page. One of these already worked out. Yep. I realized that this morning. I accidentally added that in. It's the same as this part here. So we'll work these out together. It's already worked out for you for the first two. And really, whenever we add or subtract complex numbers, we're adding the real parts together and adding the complex or the imaginary parts together. So when we look at this here, we're just adding. So we could drop the parentheses and say 4 plus 7i plus 1 minus 6i. Well, our real parts are 1 and 4. So 1 plus 4 is 5. Because 1 and 4 are like terms. 7i and negative 6i are like terms. So 7 minus 6 is 1i. And that's it. Now the textbook would probably do it a little bit differently. They would remove the parentheses, then they would group it, the real parts and the imaginary parts, kind of leaving I out, combine like terms and simplifying. This works just as well. Same thing's true for B. 1 plus 2i plus 3 minus 2i. Well, we can drop the parentheses and say 1 plus 2i plus 3 minus 2i. Well, 1 plus 3 is 4. They're like terms. 2i minus 2i is 0. So we have this here. So 4, we could say 4 plus 0i or just 4. Either one is going to be the same answer. Questions on any one of these here? So we'll do 2 more of these here, and really adding, subtracting, there's no big difference with subtraction. The only main thing we have to remember is to distribute the negative. So really what we have here is 3i. Negative and negative makes plus 2. Negative and 3i makes minus 3i. Same is true with this here. We have to distribute the negative, which gives us negative 2 minus 5i. Whenever we subtract, we do have to distribute that negative through. Now we can combine like terms. Well, positive 2 minus 2 is 0. Now, 3i minus 3i is 0. So these canceled out. These canceled out. Well, the only thing I have left is negative 5i. So incidentally, that was all that's left. Now with these addition, subtraction, we can actually do these in the graphing calculator. So in the graphing calculator, we could type it in exactly as we see it. So 3i minus parentheses negative 2 plus 3i close parentheses minus 2 plus 5i. And we just worked this one out and found out that it's negative 5i. Calculator will do it for us. So even the next one that we have, 3 plus 2i plus 4 minus I minus 7 plus I. And I'm going to type it in exactly as the problem has it. Exactly as it has it, with parentheses, everything. Exactly the same. Hit enter, and it tells us that it is 0. So the next one here is 0. Because even if we work this out, so 3 plus 2i plus 4 minus I minus 7 minus I, here, if we drop those parentheses and distribute the negative, we would get this here. Well, 3 plus 4 is 7. Minus 7 does give us 0. Negative I minus I is negative 2i. And 2i minus 2i is indeed 0. Questions on this here? Because hopefully at this point we haven't covered anything new. This should be everything you've done before. Well, the next thing that we do have is multiplication. We can multiply. And this here is just multiplying by a scalar. So we would just distribute the 4. 4 times negative 2 is going to be negative 8. 4 times positive 3i is going to be plus 12i. And that's it. And the big thing with multiplying, we just need to make sure that the I, the power of I, is not greater than 1. If it is, we'll have to simplify it down. The next one we have is this here, and we can distribute through. So we can distribute the 2. 2 times 4 is going to be 8. 2 times 3i is going to be plus 6i. We can do the same thing with negative I. Negative I times 4 is going to be negative 4i. Negative I times 3i is going to be negative 3i squared. Now I squared, we can't leave it because any value of I cannot have an exponent greater than 1. Now I squared, well, I by definition is the square root of negative 1. So when we say I squared, we're really saying that I have the square root of negative 1 squared, which is just negative 1. So for this here, well, I have negative 3 times negative 1, because I squared is negative 1. Now we can combine like terms. 6i minus 4i is going to be plus 2i. Negative 3 times negative 1. Well, the negative and negative make a positive, so really we have 8 plus 3 plus 2i. Well, 8 plus 3 is 11, and we had plus 2i. So 11 plus 2i is this multiplication. Questions on this here? Now, just like with addition, subtraction, we can do multiplication in the calculator. And it gave us the exact same answer. It will do it for us. We don't have to have it in A plus BI form. It'll do multiplication, addition, subtraction in either version. So this one here, we can do it in the calculator. So we can say 3 plus 2i times 3 minus 2i. And we get 13. Because if we did this by hand, we would distribute the 3. 3 times 3 is 9. 3 times negative 2i is going to be negative 6i. Then we do the distribute with 2i. Well, 2i times 3 is going to be plus 6i, and 2i times negative 2i is going to be negative 4i squared. And as we said on the last problem, I squared is negative 1, yes? So really what this the I squared is doing is it's really just changing that sign from negative to positive or positive to negative, because I squared is just negative 1, and negative 4 times negative 1 is just going to be positive 4. So whenever I see I squared, I normally cross it out and change the sign of the number. If it's just I squared, we can just rewrite it in as negative 1 or positive 1 depending on the sign. Now here, negative 6 plus 6 is 0, which leaves us with 9 plus 4, which is 13. Questions on this here? Even the next one. We have 3 plus 2i squared. We can do this in a calculator. 3 plus 2i squared. 5 plus 12i. Unfortunately, the 30xs won't use I. We can't use I with it, but we can use it with others. Questions on any of this here? All right. Next thing we're looking at is complex conjugates. And a complex conjugate of a complex number is just changing the sign in front of the imaginary term. If one of them's positive, the other's negative. If one of them's negative, the other's positive. And when we multiply them out, it's already written here. We end up with a squared plus b squared. All the I terms will cancel out when we multiply it by its conjugate. So we look at the first two here. So what would be the complex conjugate of 1 plus I? Exactly, it would be 1 minus I. And multiply each complex number by its conjugate. Okay. So then it wants us to do 1 plus I times 1 minus I. And again, we can do this in a calculator, and we'll get 2. So here we can say 1 plus I times 1 minus I. And that's it. Now, another way we can look at it is it also told us and worked it out, and we could have worked this out too, is that we have a squared plus b squared. And the I term is gone. So it's really looking at the number in front of I. And for our problem here, well, a is 1 and b is what? 1, yes? So we're really saying 1 squared plus 1 squared, because it's saying a squared plus b squared is what we end up getting. So 1 squared plus 1 squared is 1 plus 1, which is 2. Both ways work. Now, if we look at the next one, 4 minus 3i, its complex conjugate is 4 plus 3i. And then we just got to multiply these together to get our number. But we can plug it into the calculator and do it that way. Or we can look at this here. Well, a is 4, and the value of b is 3. It really doesn't matter what the sign is. because according to this theorem, it's really going to end up being a squared plus b squared. So we have 4 squared plus 3 squared. Well, 4 squared is 16. 3 squared is 9. So their product should be 25. So we say 4 minus 3i times 4 plus 3i. And we get 25. Questions on this here? Now, the reason we go over this is really to simplify rational expressions. Because we can't technically divide by a complex number, and we're not really supposed to have a complex number in the bottom of a fraction. So to simplify this, we multiply the top and bottom of the fraction by the complex conjugate of the denominator. So the complex conjugate of the denominator is going to be 4 plus 2i. It's going to be 4 plus 2i. So here we're going to multiply the top and bottom of this fraction by 4 plus 2i. Now if we do this for the denominator, well, 4 times 4 is 16. 4 times 2i is going to be plus 8i. Negative 2i times 4 is negative 8i. And negative 2i times 2i is going to be negative 4i squared. So we just multiplied through. We can do the same thing for the numerator. We'll do 2 times 4, which is 8. 2 times 2i is going to be plus 4i. 3i times 4 is going to be plus 12i. And 3i times 2i is going to be plus 6i squared. Any questions on this so far? Any questions on any of the steps we've done? Now the denominator, the 8i and negative 8i, will cancel. Well, we know I squared is negative 1. So in the denominator we have negative 4 times negative 1, which is really just telling us that it is plus 4. Same thing's true in the numerator, 6i squared. Well, the I squared is going to make this 6 go from positive to negative. Now we need to simplify and combine like terms. In the numerator, we have 8 minus 6, which is 2. 4i plus 12i is going to be plus 16i. 16 plus 4 is 20. Most of the time it does specify that we want to write these in a plus bi form. We want to split the fraction apart, which is not too bad. Because really all that's telling us is that we split it apart, so we'd have 2 over 20 plus 6 over 20i. So we're splitting it apart to have it in a plus bi form. We have the a, the real part, by itself, and the imaginary part by itself as well. Well, if we look at these here, they do reduce, because 2 over 20 will reduce to 1/10. Plus 6 over 20 will reduce to 3/10 i. Any questions on this so far? Good with this here? $16, yes. Thank you. So this wouldn't be 3, because 8, which would reduce again to, because 2 4/5. So we can say 4/5. And that would be the final answer, 1/10 plus 4/5 I. Yep. Now the question is also, can we do this in the calculator like we have with the rest? And yes. And when we went over these in Algebra 2, we had to rewrite it as division, as we normally 2 plus 3i divided by 4 minus 2i, which gave it to us in decimal form. Then we went math, enter to get it back to fractional form, which is the answer that we have. And the reason we had to do that is because the TI 84 Plus did not have math print that would do this here. It didn't like it. But since all of y'all are actually working with the TI 84 Plus CE, we could actually type it in. We could say 2 plus 3i over 4 minus 2i. Hit enter and it'll do it for us. We don't have to do the stepped out way because the TI 84 Plus CEs actually can do these here. So that means for us, the next problem, 2 plus I over 2 minus I, we could type it in. We could type it in exactly as we have it here. Hit enter, and it tells us that it's 3/5 plus 4/5 I. Questions on this here? So questions on this here? Almost last thing. So we're talking about this here, principal square roots. Really, we're just talking about simplifying square roots. So whenever a is a positive real number, the principal square root of negative a is defined as the square root of a. Now, for most of these here, there's some of these that we can type into the calculator, and there's some that we can't. So for the first one, square root of negative 3 times the square root of negative 12, in the graphing calculator, we do need to have it in a plus bi form. So it understands that we're taking square roots of negative numbers. So we can take square root of negative 3 times square root of negative 12. Now the graphing calculator works out very nice as long as whatever the square root number we have simplifies completely, is a perfect square. And here it tells us it's negative 6. And there's different ways we could go about solving this. One of those is looking at these individually. Square root of negative 3 is really saying that we have I square root of 3. I square root of 3 times square root of 12, negative square root of 12, well, we would have I, which does leave us with the square root of 12. Now, the square root of 12 is not a perfect square. However, the other calculator, the 30xx, if I take the square root of 12, it tells me that it is 2 square root of 3, which means square root of negative 12 is 2i square root of 3. And we can multiply these together. Well, I times 2i is going to be 2i squared. Square root of 3 times square root of 3, well, we could say that's the square root of 3 squared. Or we could say that it's the square root of 9. Either way, we're saying the exact same thing, because the square root of 9 or the square root of 3 squared is still just 3. Because the square root and square would cancel. Square root of 9 is 3. We get this here. Yes? I squared, we said, is -1. So really we're saying that this 2 is now negative. And -2 times 3 is -6. Exact same answer. And the reason this worked great in the graphing calculator is, well, all the radicals simplified out. They went away. And we need to do this here because just multiplying the two together inside the radical doesn't work as well, because the negative and negative would make a positive, and it would give us a different answer. Any questions on the first one here? So I would simplify it down and go from there. You could try plugging it into the graphing calculator first, seeing if it gives us a nice answer. If not, we'll have to work it another way. So here we can try this in the calculator. So when you say second square root of -48 minus second square root -27. Enter. So that doesn't give us a nice number. But it does tell us that we will have one term. We'll have one term left over. So if we look at this here, well, we can look at the square root of -48 first. Well, I know the negative is going to come out as I, leaving us with what? The square root of 48. The negative is going to come out as I. We're left with the square root of 48. Yes? Now we could do several different things. We could do the factor tree. We can look and start dividing by perfect squares to try to see how this simplifies. Or I can take the 30xs, type in the square root of 48, hit enter, and it tells us that it's 4 square root of 3. So that means for us that we have 4i square root of 3. Now we can look at -27. Well, we know the negative is going to come out as I, leaving us with the square root of 27. Now in the calculator, in the 30xs, we can do the same thing. Take the square root of 27 and see that it's 3 square root of 3. So that tells us that we have 3i square root of 3. Questions on this so far? Are these two like terms? Well, both of them have I squared of 3, yes? So we can combine them. 4 minus 3 is +1, which tells us that this is I squared of 3. And I just went on and typed in the square root of 3 for this here. And if we look at the decimal in front of I and that there, they are the exact same thing. So it's really telling us it is the square root of 3. But unfortunately, I have not found a good way to convert back into radical form on the 84s. There are ways to do it, but it involves a lot of graphing and more work than it's worth. Questions on this so far? Now the last one, why don't we go on and just try it in the graphing calculator, since we already have it pulled up. Well, that didn't work out nicely. But it does kind of give us a hint that we're going to have two terms. We're going to have a real part and we're going to have an imaginary part. And whatever the imaginary part is going to have that number there. I almost wonder if it's 2 square root of 3. So Now we can look at this here. So when we square something, we're really saying we're multiplying it by itself. Multiplying it by itself. Now normally I wouldn't rewrite it like this here. I would actually simplify the square root of -3. Because really what we're saying is the negative is going to come out as I. So we have I square root of 3 times -1 plus I square root of 3. Because if I can simplify any part of it, and it's not that bad to simplify, it's not too many steps, not too much to keep track of, I'll go on and do that. Then we're going to distribute through. -1 times -1 is 1. -1 times I squared of 3 is -I squared of 3. I squared of 3 times -1 is -I squared of 3. And I squared of 3 times I squared of 3. Well, we're going to have plus I squared. And what's the square root of 3 times the square root of 3? It's just 3. Because we could say the square root of 9, which simplifies to 3, or the square root of 3 squared, which is still just 3. Well, what do we know about I squared? It is -1, yes? So really it's just going to change this sign from positive to negative. Since there is a number there, we can just change the sign. We don't have to rewrite in -1, because -1 times 3 is -3. Yes? And a lot of times when I'm multiplying or doing this by hand, anytime I squared shows up on any of the steps, I go on and change it. Essentially do the multiplication of -1 and apply it there instead of letting the powers get bigger. Now at this point here we have 1 minus 3, which is -2. And that's the graphing calculator did give us that, yes? -I square root of 3 minus I square root of 3 is -2 I square root of 3. And that's it. Questions on any of this here? We're going to do one last thing. We're going to solve a quadratic equation with complex numbers. And once we do that, then we'll be done for the day. Now, we can normally look at this and try to see if we can factor it or use any other methods. But given the fact that the entire lesson today is over complex solutions, imaginary numbers, most likely this is not going to factor. So we can use the one method that does work every time, our quadratic formula. Now we look at this here, again it has to equal 0 and everything needs to be on the same side. So that we have it in the form of ax squared plus bx plus c. And then we're going to plug in for a, b, and c. Now for us here, the value of b is -2. So the first part of the equation we have is negative b, which is going to be what? -2. Well, a negative and negative make a positive, so we can write 2. If it's helpful for you to write out negative parentheses -2, close parentheses, do that. But for me at this point, I find it doing the negative is pretty easy. You can go on and simplify it. Plus or minus square root of -2 squared minus 4. This is the one part I don't simplify at all because it's a lot going on all at once. So we have -2 squared minus 4. A, in our case, is 3, and C is 5. All over 2a. Well, we said a is what? 2 times 3 is 6. So applying the negative b, applying that negative to b, and doing 2 times a, I feel are pretty nice on a whole. especially compared to b squared minus 4ac. Now at this point here, I always do this in 2 steps. Because finding out what b squared minus 4ac is here. Negative 2 squared minus 4 times 3 times 5. We can do this in either calculator. Now, I don't put the square root, and I'll show you this here, 4 times 5 times 3, because if, as we see here, the radical doesn't simplify. It's not a perfect square, we get this here. Now, we know that the 30xs does simplify radicals, so we could try typing it in here. 2 squared minus 4 times, and I know I just flipped the 5 and 3, but it doesn't make a difference. This here, again, the 30xs does not do imaginary numbers. So that's where we kind of run into an issue with both. So I find instead of typing the whole thing in with the radical, I will type and find out what it is without it. So negative 56. So in here we can say the square root of negative 56. Well, we know the negative is going to come out as I, yes? Which really leaves us with what? The square root of positive 56, yes? Now I will come over into this calculator and see what the square root of 56 is. 2 squared of 14. So really, what we have here is 2i square root of 14. Questions on this here? Are all 3 terms divisible by 2? So we can simplify that. Now for algebra 2, most of the time it was kind of the other way around. The numbers on top of the fraction were bigger than the bottom. So really what we're looking at is 2/6 plus or minus 2i square root of 14 over 6. 2 over 6 is 1/3 plus or minus square root of 14 over 3i, yes? So we could leave it as is here. Now, the denominators are still the same, yes? So the other way we could look at this is 1 plus or minus I square root of 14 over 3. Because we could have factored the 2 out of the top, simplified the 2 with the 6, and got this here. Questions on any of this here? Questions on anything we've done so far? That's it. And that is it for today. You have tomorrow also to work on this assignment.